Good evening. Welcome, ladies and gentlemen, and everyone else. The Center for Cosmology and Astroparticle Physics is proud to present the 7th annual Biard Lecture. I'll explain a little bit more about that in just a moment. And I'll also introduce our guest, Professor Julianne Dalcanton. The Center for Cosmology and Astroparticle Physics at Ohio State is designed, we have 3 missions. The first is to do pioneering research into the nature of our universe, its mysterious contents, and how that connects to physics we learn in the laboratory. Our second mission is to train the next generation of scientists to be able to carry out research in this field. And our third mission is to bring the exciting results of this research to the public, much like we're doing tonight. If you'd like to learn more about our events or how to get involved, please see our website or contact either me or our program coordinator. I'm John Beacom, the director of CCAPP, or our program coordinator, Ms. Lisa Colarosa, whose hard work and dedication made this event work. This is, as I mentioned, this is the 7th in the series. We've had a series of very distinguished scientists coming to present their work. Tonight is no exception. These people are all renowned for both their scientific research and their ability to communicate those results. And this series was endowed by Captain Forrest Biard, or Biard, who was a distinguished alumni of the Department of Physics. You should read his rather amazing story, which is in this white flyer that's available on the table outside. I can't really do it justice. And he wanted to endow us this series to help us communicate the results of this exciting research. We have a couple of representatives of the Biard family here tonight. I'd like to thank them for their support of this series. So as I mentioned, our guest is Professor Julianne Dalcanton. She's a professor of astronomy at the University of Washington. She did her undergraduate work at MIT and her graduate work at Princeton. She was a Hubble Fellow at Carnegie Observatories. And since then, she's been a professor since 1998. And she's also renowned for her scientific work, in particular for leading large, complex missions using the Hubble Space Telescope, shown here, not life-size. She's also not life-size. She is also renowned for her scientific writing to the public, including through magazine articles and through blogs. And I encourage you to look her up. She's had a lot of very interesting things to say. She's also well known in a different way. She discovered a comet, which is named after her. So not too many people get that. She actually discovered it. It's not one of the ones you buy online. So without further ado, I'd like to introduce Professor Dalcanton.
Thank you. I'm extremely happy to be here today, and watch me, I can say the Ohio State University. Did I get the D correct? But I'm told that D is very important. So I wanted to start off today with something that may be familiar to many of you. So up in this corner of this beautiful, beautiful vista, do you see the Orion constellation? Those of you who know your constellations, Orion is one of the ones that's easy to spot. However, I grew up in Pittsburgh, or as we say, the Cleveland of Western Pennsylvania. And during the time that I was growing up, Pittsburgh was not exactly known for its air quality. So my knowledge of the night sky was pretty thin. The other thing that many cities suffer from, and Columbus is no exception, is light pollution. Anytime you have ambient light, especially lights that are not shielded from above, that light goes upwards and blocks our view of the night sky. So something that could look like this, where you can see the Milky Way streaking across the sky, instead looks like this. Very, very common in cities. So growing up, I was not a big constellation person. And so to me, though, some of you may be in a very different situation, however. As you go towards darker and darker sites, the further you live from the city, you can actually see more and more. So I grew up with parents who were basically allergic to the great outdoors. So I don't think we really got past here until I went off to college. I was probably 19 or 20. So for me, I grew up with kind of this version of Orion, where you could just kind of see a couple of the very brightest stars. What I didn't realize was that if you went someplace really dark, you could see versions of Orion that looked like this. And if you go out to Yosemite or you go camping somewhere in the great outdoors, you can notice some things about Orion that you might not notice otherwise. The thing that I really want you to notice here is that the stars are not all the same color. And this is something that, again, if you go to a dark site, you let your eyes adjust and you look up, you'll start to notice not every star is exactly the same color. That's how if you ever spend time with amateur astronomers, you go out and you see something bright in the sky and they look up and they go, that's Mars. And they look so knowledgeable. You know what they're doing? Mars is kind of red. Like when you look at the sky, it's actually kind of red. And so likewise, if you look at Orion, one of the stars in the upper corner is a vastly different color than the rest of the stars. And this turns out to contain a wealth of information. And we can use these variations in color to tell us a tremendous number of things, as I'm going to explain to you over the course of the evening. Now, the way to think about this goes against all of our linguistic intuition. We're very used to the idea in linguistics. We always talk about red hot, right? Red hot. Red is hot. Blue is cold. However, in physics, nature chooses a different way. In nature, blue is actually the hottest thing. So if you think of actually like a burner, the hottest flames are those that are coming right out here. And as it goes upwards, the fire is actually cooler. So this kind of red hot isn't as hot as white hot or blue hot. So the same thing is true in stars. So it goes against what we know in terms of how we use language. But in terms of physics, the redder something is, the cooler something is. Which means that when you look at this picture of Orion, you're looking at stars that are actually different temperatures. And when you look at a picture like this, just by looking at it, you can figure out that this star, the surface of this star is hotter than the surface of this star, this is amazing, right? All you did was you take a picture of it. You didn't have to send some spacecraft out there with an interstellar thermometer and stick it in the atmosphere and measure it. You can just look at it and say, that one's redder than that one. This one's cooler than that one. And that's amazing. That's an amazing factor. We're going to come back to this because there's additional information besides just the color that we can use to learn something more about these stars. Now, there's something else that I want you to notice here. So first of all, we've noticed that the stars are different colors. The other thing you may notice about Orion, so Orion's got his belt. He wears one of these manly Grecian tunics. And he carries his little Jedi lightsaber. Well, he's on his side. He wears it to sleep, apparently. And so here's his sword. And if you look at one of if you're at the Columbus, you can see maybe 3 stars in the sword. But if you look at one of them, it doesn't really look like a star. It's actually kind of extended. Okay? That little blob there is no longer a little point source from a distant star. It's something different. And what this is that this is actually a birthplace of stars. So to learn, we're going to get back to the story of stars' different colors. But to talk about it, we're going to actually start talking about the entire life cycle of stars. We're used to thinking about stars as being something that are just up there. You go outside, and there they are, and they're always there. And maybe you've heard stories about supernova, but that's kind of about it. But stars are actually part of a large ecosystem where stars are born, stars evolve and change over their lifetimes, well before they ever undergo a supernova. And so places like this place that we think is a star when we look at a constellation, is actually a place where stars are currently being born, which is, again, really amazing and not something you necessarily notice when you just are looking up at the night sky. So this is a picture of the Orion Nebula taken by people who get to use really big telescopes and dedicate a lot of time to making these kinds of images. So this is not something you can see with your night sky, not even, no matter how far out in rural Ohio you go. But it shows a lot of wonderful details. So you can see the basic structure of Orion. You can see the different colors of the stars. But you can also see this glowing red gas everywhere. When we talk about galaxies, most people have some idea, and especially the kind of people who would come out on a night like tonight to listen to me yak at you, have some idea that galaxies are made up of stars. What people may be less familiar with is that galaxies also contain a lot of gas. And that gas is the fuel for star formation, and that gas is something that is affected by the stars. All of this red gas is very, very hot gas that has basically been raised in temperature by very, very young stars. And so this red gas everywhere is signs of some of the young stars that are being formed. So we're going to look right in here. This region right here is known as the Orion Nebula for obvious reasons. And it gets better and better and better the more you look at it. Now the first question you might want to ask is, why are stars forming here? Why is this region so bright? And why have stars chosen to form here? And the reason is this gas that pervades the galaxy. Now all that red glowing gas is very, very hot, But there's also gas in the galaxy that's extremely cold and very, very dense. It's so cold it's only 10 degrees above absolute zero, which by most, even astronomers, consider that to be pretty cold. This image is showing flipping back and forth between what the night sky looks like, and if you were able to put on your goggles that let you see that very, very cold gas, where it would be. And you can see that most of the star formation, where all these stars are forming in this nebula, is concentrated right where there's the most amount of this very, very cold gas. So what happens is you have this cold gas, it's barely moving, it's very, very, very dense, and it's so dense that sometimes you get little lumps in it. And those lumps have enough gravity that they can pull themselves together to higher and higher and higher densities, smaller and smaller regions, and eventually ignite and form a star. So that very cold, dense gas is the immediate precursor that it takes to actually form stars. Now, this very cold, dense gas, now you can use very special telescopes to see this gas, but there's another trick I want you to use in your head as we look at some of these images, which is that this very cold, dense gas is often associated with dust, which is something people really don't necessarily think of as being a component of galaxies. Galaxies contain they're the equivalent of soot or sand particles. There's many different kinds of these tiny little particles that block the view of background light, and you tend to find all of this cosmic dust coupled to this very, very cold, dense gas. So wherever you have cold, dense gas, you'll often see these black clouds associated with it. So in the images that follow, anytime you see this kind of black emission blocking the background view, think to yourself, oh, that's probably where I see cold, dense gas. It's actually dust, but it's a pretty good hint that some of that cold, dense gas is there. These are globules, which are very, very small compared to what I just showed you, but it gives a good visual description of what you might see. Okay, so now we're going to zoom in on this region. It gets more and more spectacular. Okay, so this is what you might find if you had a pretty big backyard telescope with a camera on it and you took some long exposures, you might be able to make something that looks like this. And so you can see a couple of things. You can see all of this very, very hot gas, like what we saw in that first image with all that red stuff. It gets very, very intense here. And then you can also see the black dust that's obscuring things, and that's where all of that cold, dense gas is. And so you can see this very, very hot gas and this very cold, dense gas are all coupled together in the same region. Now, if you look right in that center region with the Hubble Space Telescope, it looks like this. And if you get tired of looking at this, I'm worried about you, because this is really, it's the best screensaver ever. It's wonderful. Okay, and if you look right in this region, right here, okay, so we're zooming farther and farther in on the night sky. If you look right in this region right here, two different ways. You can look at it with a telescope that sees, with a camera that sees visible light, just like your eyes might see. And you can also look at it with a telescope that looks at it's called infrared light. So it's the same kind of wavelengths of light that you might use in night vision goggles. But it has a special property that allows you to see through all of that dust. So if we zoom in on here, this is what it looks like through sort of normal eyeballs if you could attach them to a telescope. And this is what it looks like if you look at special kinds of light that allow you to see through the dust. And you can see that there's this little cluster of stars right in the center of this. So this whole mess, right, this huge, enormous mess of very, very hot gas that's being converted from this very, very cold gas is because of this little population of stars that's forming right in the heart of this. It's an amazing thing. This is just going on. This happened, in astronomy speak, this is only a few million years ago. It's very fast. Okay. So I just want to show you these star-forming regions. They just happen to be some of like the nicest looking things in space, so we're just going to look at a few of them. Okay, so what happens is stars will form in this very dense cold gas. Again, we're tracing it by looking at these kind of dusty regions. And so you'll have these stars that are born in this dark cocoon of very, very cold, dense gas. But once the star lights up, it's bad news for that cold, dense gas, and it starts to destroy it. So all of this glowing stuff you see around is the hot gas. And that hot gas is what you get if you start with cold, dense gas, you turn on some bright stars, those stars just do all kinds of damage, they wreck their poor home, it's very sad, and then they light everything up. Okay, so you're going to see this process. They also, do you see those little trails up there? Some of these young stars also send out jets of material that then bombard the surrounding parts of it. So again, you can see this region here is very rich in that cold, dense gas from which the stars were born. And then gradually, these young stars that are up there are eating away at all this cold, dense gas, turning it to very, very hot gas. Here's another one where you can see those jets really clearly. Isn't this awesome? Right, you see those jets up there. And again, the same process of this whole region being obliterated by the young stars. I love this picture because it really shows the process. There's one very, very massive bright star right in the center of this region of this very cold, dense gas. And do you see the damage it's doing? It's just blowing these huge bubbles of just destroying the surrounding area. Okay, so this cycle of star birth changes everything about what's going on within the galaxy. Now, gradually what happens is as these stars destroy all the surrounding gas, you reveal this cluster of stars inside. So in the same way when we could peer deep inside the Orion Nebula, you saw there were a bunch of stars there. Some were bright, some were faint. This is a very general picture. When stars form, they rarely form alone. They typically form in a group, what we call a cluster or an association, where you have very few bright stars and tons and tons and tons of little stars. And what this is a group of stars. They all have a wide range of masses. In general, these tend to be the most massive stars, and the fainter ones tend to be the less massive stars. But they all form at the same time from the same cloud of gas. If this process goes on, eventually all the gas is gone. You've lost all of that cold, dense gas, and you also lost that very, very hot gas that was all around, and you're left with just this naked cluster of stars that's fully emerged from this. Okay, so that's the whole cycle. That's the equivalent of the 9 months of gestation. And what you get out of it is you get a whole bunch of stars that all share a common age, but a wide range of masses. And so now I'm going to show you the coolest thing for me about these stars. And you may not think it's cool because I'm going to show you a graph, okay? But it's a really cool graph, okay? If you take the star, no, but trust me, you're going to like it by the end of it. If you take this group of stars, and each star, come on, computer. There we go. If you take one star and you plot it on this graph where along this axis you plot the color of the star, which as we know is the temperature. So cool red stars over here, hot blue stars over here. And this is a plot of the brightness of the star. These are going to be our faint, lower mass stars. Those are going to be our bright, high luminosity stars. If you plot that star, it's going to live somewhere around there. If you plot that star, it's going to live it around there. And if I do this for every single star there, they're all the same age, wide range of masses. I'm going to populate this entire sequence from there to there. Now, why is this amazing? Okay, it's a line on a plot. Why is it a line? Why can't it just be? Why don't I have stars here? Why don't I have stars here? Why is it that I've just gone through all of these crazy things inside this cold, dense gas cloud, how come at the end of it, all my stars lay right there? I mean, that's pretty cool, okay? It could be anywhere. So I'm going to tell you why. And this is even cooler. So just so you know, you may wonder when I look at this, how come I don't see super faint red stars? They're just too faint. They're kind of hard to see. So a lot of what I'm going to show you, you may not notice the huge color variation unless we've really tweaked with the images. Okay, so a lot of times this stuff here, we're not going to see it. All right, sometimes we will, but most of the time we're not. Okay, so what's going on? This turns out to be this beautiful sequence, and the astronomers call it the main sequence. This is how important we think it is to us. It's the main sequence. The reason this sequence exists is that stars inside have this absolutely exquisite, finely tuned balance that they just naturally do. If you think about a star, they're pretty big. There's a lot of mass in a star. Okay, you could fit it takes a whole lot of Earths to make up the mass of the sun. And like everything, there's gravity. And stars are not solid. They're basically big balls of gas. Okay? It's this big ball of gas. It's not solid. You know, the Earth is rocky, and so gravity pulls me in, but the rockiness stops me. Whereas this ball of gas, there's no surface to stop the stuff from falling in. What stops it is the fact that the gas inside is moving around so fast that it can actually push on the gas outside. And this is called pressure. So it's the same thing if you've talked about gases in chemistry and talked about pressure. This is what it is. It's just the pressure pushing outwards. And so a star finds an equilibrium point where it's perfectly in balance between gravity pulling the stuff in and the pressure of the gas pulling it out. But if you think about it, it's much like these poor, unfortunate, this poor guy, right? Can you see on the expression of his face? He's really suffering. He has to hold up the whole weight of everything above him. Likewise, in the interior of a star, it has to effectively have enough oomph upward that it can support the entire weight of the star coming down on it. So the pressures have to be really, really high, which means in here, the gas is very, very concentrated because it's got all of this weight of the star pressing it inward. Okay? And so inside the sun, and this is the sun, which is just kind of a run-of-the-mill star. It's not even a really big one. The center of the sun is a lead brick. And ordinarily, I would drop this brick about now, but the floor up here is beautiful. I'm not going to do it. Okay, but I'm going to, can you see? It's really, watch it, okay. Okay. Center of the sun is 15 times denser than that lead brick. Okay, that's pretty dense. However, it's denser than a lead brick, and yet it's a gas. It's not solid. And the reason it's doing that is it's so incredibly hot that the particles are moving around incredibly fast, which they need to be. If they're going to, if they're going to hold up that whole weight, the particles have to be moving very, very fast. So in here, for this whole system to work, you have to have the center of the star be incredibly hot. Okay. Now, this is the magic about why you can keep this star. How do you get the center of the star really hot? And this was a topic of a lot of debate for quite a while. And what they eventually figured out is that inside the very center, what we call the core, you have such a high density of matter, right? You've got 15 times the density of a lead brick. And you have all of these hydrogen atoms. They're basically just naked protons. And protons are positively charged. And so if you take two magnets and you try to push them together, and you know how they repel each other? Same kind of thing if you take naked protons. They don't want to be anywhere near each other. And if you try to get them near each other here, they're just going to ricochet off. However, in here, it's so dense and it's so hot that the particles are moving so fast they don't really have time to get out of each other's way. They can get close enough that you can get multiple protons that merge together and form a nucleus of helium. They can actually form a new element inside the center of a star like the sun. Okay? And this process releases stuff, and that stuff is indirectly responsible. It releases energy, and that energy is the source of all of the heat that we have keeping this central core hot. Okay, so it's this amazing thing that the star is doing. Now, this balance of everything depends only on the mass of the star. So every star of a different mass finds a new special space for itself, where these things are in perfect balance. And that sets how bright the star is, which is basically how much energy is being made here every second, and exactly what structure the star sets, which sets the temperature on the surface. So this exquisite balance of all this stuff, it's got nuclear reactions in the core of stuff. It's crazy. It all sets the color and the brightness of the stars that come out of it. So the net result of this is this beautiful sequence where the massive stars wind up blue and bright. However, there's a flaw in the plan. Okay? If you look at real data, so this is our nice little thing that I stole from a wonderful textbook. Here's real stars near our own sun. And you can see it. That looks pretty good. I mean, there's a few bumps and wiggles, but the basic idea is sound. But through the magic of PowerPoint, I've erased part of what's going on. Okay? That there's a whole bunch of other stars that aren't obeying this relationship. Right? I just told you there's this beautiful balance when they're taking hydrogen and merging it to form helium in their core. Stars live along this sequence. Can we take a second to appreciate that? Just by looking at the color and the luminosity, I can tell you what this thing is doing in the very center of it, which is amazing. Okay? But then, what's up with those guys? Okay? here's the problem, is that this process means you have to have these nuclei of hydrogen. Okay, the same way when you drive your car, you need to have gas in your car in order to go anywhere. You need this as fuel to drive this whole process. Eventually it runs out, right? If I drive my car for long enough on I-70, you know, I'm going to wind up on the outskirts of Louisville with nowhere to go. Okay, so when this goes away, all of a sudden, this can't happen, which means this exquisite balance is broken. Okay, and you can't live on that nice, happy sequence anymore. All kinds of things are going to start to happen. So suddenly, if I turn off this power source in the center, all of this stuff is going to come rushing inwards. And as it comes rushing inwards, there's going to be all sorts of readjustments. And you can have a whole graduate course in stellar evolution to talk about that. So I'm not going to talk about it right now. But just the star is going to try to find, it's going to temporarily find other ways of burning fuel. It may eventually explode. All kinds of things happen. But one of the things that happen is that you make those stars over there. And we'll see a little bit more of those in the future. Now, the other thing that's kind of interesting about this is that these are stars of all different masses. But these stars that are very, very luminous, these are like, you know, a performance race car. They're not real fuel efficient. So they do amazing things. They're very, very, very bright. They're very, very hot. But they are using up that hydrogen at an incredible rate. So those stars up there live a very short time, astronomically speaking. Okay? And so those stars will disappear. But if you wait a while, the lower mass stars are going to disappear. And you wait a while after that, even lower mass stars are going to disappear. And then even lower mass stars. And so over the age of the universe, stars like the sun will eventually run out of hydrogen. And someday the sun is going to run out of hydrogen, and it's going to go through all of those kinds of crazy things. So what this means is this, by looking at this combination of color and luminosity, you're getting some information about timescales over which stars did things. So if I look at a group of stars and I see stars here, but I don't see any stars here, I know that's a group of stars from well in the past. Whereas if I see stars where I see them all the way up to the bluest, brightest, hottest, most massive stars, those stars have such short lifetimes, astronomically speaking, that I know that they basically formed yesterday, astronomically speaking. Okay? So how stars are distributed here gives you this way of actually probing the entire history of when stars formed. So it's this beautiful archaeological tool that we can use to read the past in what we see. So I'm going to sneak in another plot. This is the same plot, but just different. Okay? This is color. This is how bright the stars are. So bright up here, faint up here. And what I'm showing you is what happens when you look at groups of stars formed at different times. When we look at a galaxy, they didn't all form their stars at exactly the same time. You see stars of many different ages from many different generations. The most recently formed stars will be all the way those very, very hot blue stars. But the older stars are going to be ones that have run out of fuel. They're going to be fainter, and they will have formed all those crazy redder stars that populated that diagram. So this shows you how stars of a given age, if I just look at a bunch of stars that have one age, how does that population look in color versus luminosity? And what this shows is as I build this up and I form stars at every possible age, this whole plane of color versus brightness starts to be occupied. But it's not occupied randomly. It's that same idea that not any star gets to live anywhere. There's certain regions where you only see older stars. And then there's other regions where you only see the younger stars. So when you look at a field like this, you see stars of different luminosities, brightnesses. You see stars of different colors and temperatures. You see bright blue ones, like those guys over there. You see bright blue ones, like those younger ones over here. And if I take a plot and I just measure all the properties of all these stars and plot their brightness versus their color, and I've had to use some contours because there's so many stars, and I'm just plotting the kind of density of things. you can see this is that tail end of those bright stars on that main sequence where stars are just burning hydrogen in their very centers. And then these are those crazy red stars that result when they use up their main source of fuel. And in general, anytime you see something over there, it's kind of younger. And when you see something over here, it's older. So if I show you a plot like this, just think a lot of blue stuff is probably young. A lot of red stuff is probably old. Okay? Now, the thing about this, now I want you to take, you now know enough about stars to kind of start piecing together some of the magic that's going to happen. The next thing I want you to think about is what happens when you look at a galaxy. I don't know, some of you are old enough to have seen Cosmos, and Carl Sagan was well known for his billions and billions. Okay, when you look at a galaxy, what you are seeing are billions and billions of stars, all at once, all at the same time, with all of their light blended together. So when I look at all of the stars in a galaxy, I'm seeing mixtures of these stars, and 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 these stars, all together. And so when I look at the galaxy, it just looks like a certain color. And that color is the result of all of these individual stars that make it up. So if I look at a galaxy and it looks mostly red, it probably doesn't have too much of this. And so I can look at that galaxy and say, well, it's kind of an old galaxy. If I look at a star and it looks very blue, it means that this part of the diagram has tons of stuff in it. I can say, probably a lot of young stars in that galaxy. So you get to the point where if you understand what's happening with the individual stars and their colors and their brightnesses, you can start to look at any image of a galaxy that you might see in the newspaper or your screensaver and look at it and say, it's pretty old in that inner part right there. Okay, just by looking at the color, because you can think about how all of this stuff, all of these individual stars blend together to form the total image that you see. So here's an example. I love this picture. Here. This is ARP 273. ARP has an atlas of peculiar galaxies where he just looked at all the images of the sky and he just made a catalog of things that look weird. This was one of them. So you can look at this. Big red regions probably have lots of old stars. Look at all these blue regions out here. That's probably where the young stars are. So you've come a long way. I've been talking for about half an hour, and you can already look at this and just kind of figure out what's going on, which is, again, really cool. Okay. Now this is something called the Hubble Deep Field, which is one of the, or this is the extreme deep field. This is one of the deepest exposures that's ever been taken of the night sky. Every single one of these galaxies has billions and billions of stars in it. Okay, so all of that light that we see is made up of all of those individual stars, each doing their little dance of, for my mass, where's my color and luminosity? How does that change depending on the mass that I am or how old I am? For billions of stars in each one of these to produce this kind of view. It's unbelievable. There's galaxies like this one. You just look at this. This is young or old. Okay, very red. You don't see all that beautiful blue lumpiness. Galaxy like this, all those little blue lumps. Oh, do you see this stuff? That's more of that dust. So that's that cold gas showing up again. So again, you guys know all kinds of stuff now. All right. There's galaxies like this one that are just really weird. This is actually kind of nifty. All this blue stuff, that's all that gas, kind of like you saw in the Orion Nebula, but it's now on the scale of an entire galaxy. Kind of amazing. Okay. So what we want to do is to be able to try to understand these galaxies, using these tools of understanding the individual stars within them, and to use this information to pick apart the archaeological record of how these galaxies formed. And one of the reasons you want to do this is that we think that the kind of material that you see with your eyes when you look at a galaxy is a very small fraction of all the material that's out there. We think that actually most of the mass in the universe is this dark matter. And we know the dark matter is there because it pulls on things and makes things move. So we know it's there. If I had a glow stick and we turned off all the lights, I attached the glow stick to a string, and I swung it around in a circle, you could figure out that there was a string there based upon how things were moving. We can look at how a galaxy moves and figure out that there's a lot of mass in the galaxy that we can't actually account for. And we think it's this dark matter. And there's theories, and these are the kinds of things that are studied here, at the Ohio State University. They can study this dark matter. But when we look at real life, it doesn't really look like this. Here, there's tons. We think that the dark matter is very clumpy with lots of little knots. But when we look at real galaxies, they have these kind of faint little satellite galaxies, but we don't see hundreds of little knots. So there's something that's going on in the universe that takes what we try to infer about what this dark universe is doing and changes it into the view that we actually see. And there are theoretical models for this, and typically this is a complex process. So we basically plug the rules into a computer. It looks exactly like this. And then we take models for this, the computer does its thing, and then it spits out stuff at the other end. I'm going to show you a movie of this. This is what some of my colleagues at University of Washington are experts in this. So this is showing what's happening with gas. That was the initial expansion not too long after the Big Bang of all the gas in the universe. And then gravity and the dark matter is pulling everything back in. When you see these pink and blue stuff, those are stars that are being formed from that gas. And you can see early on, we think the evolution of a galaxy is a very messy business with lots of little knots coming together, continual mergers and interactions of small pieces. You can see gradually things starting to spin, structure forms, and then gets destroyed because something just comes and plows into it. And this is a process that's controlled by the gravity of the dark matter pulling things in, and the effect on the normal matter that we actually see, plus the effect of star formation back on the gas. You saw how star formation did horrible, horrible things to that gas that was around it. The same thing happens on the scale of galaxies. That star formation really affects the subsequent evolution of what we see. Now, after a lot of time, you can think things are starting to settle down. Oh, not, but then somebody comes along. Okay? And so this process of gradually forming a large, right, this is gradually forming a large disk galaxy like the Milky Way is a very long, involved process with many episodes, very complicated, chaotic history. And you can see there's a lot of physics that goes into doing this. And the state of the art for these simulations is wonderful. They make things that really look like real galaxies. Okay? And this is wonderful. We feel fantastic about it. And it just doesn't mean it's right. Okay? There's a lot of steps. And I can tell a convincing story that movie, which is all happening inside a computer, is the right story. It doesn't mean it's right. So you have to go out and actually test this stuff. And one of the ways that you can actually test this is using these individual stars. So those models make predictions for how old galaxies are, how different parts of the galaxy formed. You could see on that movie that the inner parts assembled much earlier. That big disk didn't really form until quite late. So you would expect when I look at a galaxy, the outer parts are going to be on average younger than the inner parts. Right? There are very specific predictions you can make. Now you guys are now amateur astrophysicists and can look at the galaxy and say, well, those parts are old, those parts are young. But if you want to take it one step further, you want to be able to actually see the individual stars. You want to do a little better than this part's red, this part's blue. Okay? So how do you actually untangle all of that light blended together with the galaxies to see the individual stars within it? And to do that, you do the Hubble Space Telescope. And the Hubble Space Telescope is awesome. Okay, now, the Hubble Space Telescope is an idea that was long in development. So in the people talked about this concept as early as the 1920s. There's a very influential paper by Lyman Spitzers in the mid-1940s where he talked about the astronomical advantages of an extraterrestrial observatory. And he goes through all the various arguments why this might be a good thing to have. It gradually became a real project sometime in the 1970s. By 1981, here's a beautiful drawing by Lockheed Martin. This was, hand shaded, right? This is not CAD/CAM on your map. This is with a ruler and everything doing this stuff. It's pretty amazing. This was not that long ago. Okay. So originally, this was planned to launch in 1986. There was a cold, very, very cold day, unfortunately, in early 1986, where the space shuttle exploded. So the idea was that the Hubble Space Telescope was going to be launched by the space shuttle. But earlier that year, the shuttle went up on a day that was too cold, and part of the fuel tanks breached. There was an explosion. all the astronauts were killed, and the shuttle program ground to a halt indefinitely until they could analyze what happened and make sure they fixed it. So this didn't happen. Okay? So they've got this telescope. It's ready to go. Okay? And it's just in storage. Storage through 87, 88, 89. Finally, we're able to launch it in 1990. Okay. So it was launched off a space shuttle. And since then, part of the idea of launching it with the space shuttle was that the space shuttle could then go back, capture it, and do repairs on it. And so they did more than just fix things. They also put new cameras on, new instruments. So even though it's a very old device, it was ready to go in 1986. Very, very old device. They've been able to kind of take good care of it by sending the astronauts up. One of the astronauts who worked on it in the most recent servicing mission, he got through MIT by repairing old Jaguars. I used to repair old Volkswagens, and you know how you always need a breaker bar because all of the bolts are seized? Same thing happened. They couldn't get one of the cameras out. But it was great. They had the old Jaguar repairman, right? And it was, they kept on using higher and higher torque settings that had all been approved by NASA engineers. And eventually, none of it was working. And he's like, well, how hard should I do it? They're like, and so it was just, and it's great. And he wailed on it, and it came out, and everything was great. So I just love, they prepare for everything, but they didn't prepare for that. But they had exactly the right guy doing the job. So anyway, so these refurbishing missions have kept it operational and fresh for over 20 years, right? 1990, that was a while ago. Now, what makes Hubble special? It's not that big, okay? This grayish image in the back, this is the Keck telescope. This is currently one of the largest ground-based telescopes here on Earth. And when I use ground-based, it distinguishes it from a satellite that's orbiting us. So Hubble, Hubble's 2.5 meters across. Like you could hug it. Okay, the mirror is not that big, and the mirror is what matters for how sensitive a telescope is. The bigger the telescope is, the more light you can capture from the universe, and you can see fainter things further away. So bigger is usually the metric by which we think about telescopes being awesome. And you would think, oh, this is great. Why would I ever need dinky little Hubble? Okay. The key is that Hubble is above all of the Earth's atmosphere. So the number one problem in terms of seeing stars in other galaxies is the fact that if you look through the Earth's atmosphere, it blurs images of distant stars. So have you guys ever driven on a hot road and you see that blurring of distant stuff? That's the atmosphere moving off the hot road and kind of going up, and it's turbulent stuff is moving around, and it blurs the images. This happens at a small effect when you look upwards, even on a cold night. So stars twinkling, that twinkling are little changes in the density of the upper atmosphere that move the position of the star. And so a star that should be a tiny, tiny little point on the sky, very quickly, this is showing how the atmosphere moves this over the course of seconds. And it tends to blur things out. So if you had a very, very fast exposure, maybe you could isolate this and the stars would look very tiny. But because the atmosphere makes this twinkling happen, the star gets smeared out. And that's a bummer. If you're trying to pick out individual stars, it's blurring with all of the neighboring things. So this is what happens. This is what you get with a ground-based telescope. And this is what you get with Hubble. Right? So compare, this is 10 times the angular resolution. So if you think about an eye chart, this is seeing the big E. Okay? This is that LPZ on the bottom row. Okay? You can see a tremendous level of detail here that you can't. The other benefits are that by being above the Earth's atmosphere, you can also see different wavelengths of light that you can't really see on the ground because they get absorbed by the Earth's atmosphere. But that's less important for seeing the stars. Okay, so here's what it looks like for seeing individual stars. Here's an image of a cluster of stars as it looks like from the ground. And this is what it looks like from the Hubble Space Telescope. If I slip and I use the word HST, that's how we often talk, because we're on kind of buddy-buddy nickname basis with the Hubble Space Telescope, and we call it HST. Okay, so this is how it looks like with Hubble. And look, bright red stars, bright blue stars, all those things that you've seen. You can already take a look at this and see. Now, because this is a stellar cluster, a group of stars all born at the same age, what you're seeing are a bunch of stars that are still burning hydrogen in their core, And then these red stars are those ones that have gone crazy and have run out of fuel. So you can look at that distribution and figure out how old this little group of stars is and when it actually formed. You can start to see how you might start being able to piece together all of the history we have here. Here is a Hubble Space Telescope image of a galaxy. And if you squint, it looks like something you would actually take from a normal telescope on the ground. But you see how speckled it is? That's speckling. Can you guys see? OK. I can see it here, but it's a lot easier for me. That speckling is that galaxy, not instead looking at the smooth light of all those billions of stars blurred together. They're now breaking up into their individual points. Here you can see it a little bit better. This is an image taken by my team of ANGST 247. And you see how there's a blue spot there. There's a green spot there. White spots there. Red spots there. Okay? This is a huge galaxy being broken down into individual stars that we can measure. Whoa. This is a zoom in to a ground-based image, then going into the Hubble Space Telescope images that we took. There's a bright nucleus in the center. Whoa. And then you can see all the changes in the mix of stars. Do you see how there's different numbers of red stars and blue stars? These green regions that go by, those are those regions like the Orion Nebula. Zooming by, there's places where you can see background galaxies. Those are some more of those Orion Nebula kinds of things. Bright red stars, bright blue. Oh, this is a background galaxy. Okay, many, many miles away. Not miles. You know, okay? So this shows you how that, let's just go back. That should have been on repeat. Okay, so there's just a standard ground-based image. There we go. And then fading in, and you see all that detail being revealed. Okay, and that's what you get from the Hubble Space Telescope. The ability to pick that apart into all the little constituent stars. We can't see all of them. Lots of the stars are way too faint for us to see. Remember how I said we don't see the bottom half of the image? We just see the bright ones. But there's so much. If you can't do science with this, you're not trying. Okay, there's so much information here. All right. Now this is a movie that one of my former students made, where what she's done is this is that same strip that we just panned through. And then in regions, she's making this plot of color versus how bright the stars are. And if you remember, stuff over here is young, stuff over here tends to be older. And you see as you go outwards, you can see the relative strengths of these different regions change. And we can analyze, we can model each one of these in great detail and actually solve for the real history of how did star formation happen here versus here versus here versus here. And we're actually now, we can make movies where we break this up into little chunks and then just play the movie of how this galaxy formed its stars, which gives us a whole new bit of leverage on trying to understand the science of how galaxies form and evolve. Now, this is there's a wonderful astrophotographer named Robert Gendler, and he took some of our HST images and made this absolutely beautiful, somewhat lurid picture of ANGST 253, which is a relatively massive galaxy. Many of the galaxies that are nearby that we can study are relatively low mass, much smaller galaxies than the Milky Way. This one is pretty massive. But if you look at this, it's not that modeled, right? That modeling that we saw where we could break things up into individual stars, in more massive galaxies, their stars tend to be packed much closer together. And so it's harder to see spaces in between the stars because they're, it's like if you're at a concert and everybody's packed standing room only and you're squeezed in there. It's a lot harder to pick out your friend than if there's, a couple people in a large room. Same sort of thing here. These massive galaxies, the stars are so close together, we can't see them. And we really want to understand massive galaxies. So when we look at those very deep images of the distant universe, those galaxies are so far away, we can only see the brightest, most luminous galaxies that are out there that tend to be the most massive. So if we want to understand the nearby analogs, the archaeological record of the kinds of things we can see very far away when we're basically looking at galaxies when they were quite young, we want to be able to do massive galaxies. So why not use the Milky Way? Milky Way is a massive galaxy. That would be really good. But here's the problem. There's two problems, actually. The first one is distance. The problem with the Milky Way is that we live in it. Okay. So those plots that show you color versus how bright the stars are, there's a little trick in there. And the trick is that you need to know how far the stars are. Okay, here are my two stars. I traveled with this. This made it through the TSA, just for you guys. Okay? I can hold these up here, and this one's a lot brighter than this one. And you can tell this is brighter, not only because you can see its girth, but even if I were just pointing it at you guys, okay? You could see that this one was much brighter. However, what if I took this one, and I walked up to you, and I can't because there's this ledge, and I would hurt myself. And I walked up, and I just shoved this right in your face like that. It would look pretty darn bright. It would look a lot brighter than this. So if you don't know how far away something is, you can't tell just by looking at it how bright it is. And so in the Milky Way, it's a huge pain in the butt. Like you look at all of these stars, this one could be the faintest star in the world sitting right next to us. Okay? And these little smudges you could barely see could be the most luminous star in the whole galaxy, but just really far away. So trying to do this kind of work in the Milky Way is not something I personally wish to do. Okay? That's the first thing. Second thing is dust. Look at all this stuff. Do you want to look through that? I can't look through that. Okay, so the dust is a real problem, and that's because we're in the middle of this a galaxy that's kind of like a frisbee, and we're sort of living in the middle of the frisbee. So when I want to try to look towards the center of the galaxy, all of that cold, dense gas gets in my way, and I can't really see. So trying to do this in the Milky Way is hard. The Milky Way is massive, which is great, but this kind of work's tough. Well, it turns out one of the ways that you can get around this problem where these massive galaxies can't, you can't see between the stars is to bring the galaxy really close. Because two stars that look close together on the sky when something is far away, as you get closer and closer and closer to you, you'll get more separation between them. So the key is to try to find a massive galaxy that's really, really close. Milky Way is not going to work. We do have a couple of very close galaxies. These are the Magellanic Clouds. So I didn't know, again, I went to graduate school in astrophysics. I didn't know this until I got to graduate school. We have companion galaxies that orbit around the Milky Way, and you can see them with your naked eye if you go south of the equator. It's the most amazing thing. I used to go observing in Chile a lot, and one of the night assistants, you spend a lot of time talking about the weather. I know a lot of Spanish words for weather. And the night assistant, he'd go out on the catwalk, and you try to judge clouds. These are very dark places. It's hard to see if it's cloudy at night. And he'd come back in, and I'd say, "How's the weather?" And he'd say, "Dos nubes," which means two clouds, because these are known as the Magellanic Clouds. So that was his little joke. Okay, it was dark enough you could actually see the two clouds. But these are very small galaxies. They're puny. Really, they're not so great for doing this. These are not examples of the massive galaxies we need. So here's a map of all the galaxies that are really close to us. This is a region called the local group. Milky Way is here, and we have all these little faint guys all around us. Again, they're faint, not that interesting. But right over here, we have the Andromeda Galaxy. The Andromeda Galaxy is very likely even more massive than the Milky Way, though people argue about it. And it's really pretty close to it. It's much closer than some of those images I showed you previously. So this is great. Okay? Now this is something you can actually see. You can see the center of this galaxy with your naked eye. In the same way you could see those Magellanic Clouds if you went south of the equator. This is something you can actually see from where you are in Columbia. I mean, not here, because there's a roof, but you have to go way out of the city at night. Right? Where is it? That little smudge right there, that's the Andromeda Galaxy. Okay, this is another one of these things that looks like a star. It's not actually a star. And it looks tiny there. And it looks tiny there because you're just seeing that little bit of it. That's very, very, what we call high surface brightness. A lot of light in a small area. And that's the part you can pick out with your eye. But if you take a telescope or a camera, you can actually see that this thing is actually huge. It's many times the width of the full moon. So that's great because it means all the stars in the galaxy are really spread out apart from each other, okay, because they're distributed all across the sky. It's bad because it's huge, okay? When you take a picture with a telescope, you get a little view of it. In particular, with the Hubble Space Telescope. This is a very, very big deal. So a couple of years ago, the Hubble Space Telescope, it's more than 20 years old. And they said, are there any things we should do with this that we're going to regret that we hadn't done if the telescope drops into the ocean, because it's old. Okay, something could happen to it. Are there going to be things that we wish we had done, but are nuts? I'm like, I can do that, okay? And so what we proposed to do was to map out this huge region of the Andromeda Galaxy with the Hubble Space Telescope. This was nuts, okay? And we got the second largest allocation of Hubble Space Telescope time ever in the history. And it took 3 years to get all the data. This is all, there are certain times of the year, the Hubble telescope, right, that's all, you know, it's just sitting there taking all of the images for this program. We just finished it up in October, so it's now, everybody else gets to use it again. This is the reason it's nuts, okay? This is the region we want to survey. This is the field of view of a typical Hubble Space Telescope image. It's like if you take a quarter and you hold it out at arm's length. The width, the height of that quarter, not like the round way, but on its side. That's kind of the size of the Hubble Space Telescope field of view. Yeah, and this is bigger than the full moon. Okay. We take images in a bunch of different wavelengths with a bunch of different cameras. Usually we take images in one camera at the same time we take images in another camera, so we're very efficient about this. And eventually we get we look at 6 different regions of color for the galaxy. We look at very, very red light all the way up to very high energy ultraviolet light. And we develop this panchromatic view of this galaxy where it's so close that we can see the really, really faint stars within it, okay? Now, the current status, this is the whole area we've done. Can you see that there's little lines in here? Each one of those is an image that we took. This was crazy. I can't believe it did. The very first large program I ever did with the Hubble, the camera literally, part of it exploded 4 months into it. So I can't believe we actually finished this. We have close to 1 terabyte of raw data, close to 10,000 images. We have measurements for more than 150 million stars, which I prefer to say is 0.15 billion. And then, you know, when you add up all the different things we measured for these, we have probably more than 1 billion different measurements that we made over the course of this project. It's a big computer project. We have to run this on the Amazon cloud because you just can't run it on your laptop anymore. Now, when you put together all these images, you know what it's going to look like? It's going to look like an ordinary image of the Andromeda Galaxy, right? I mean, it doesn't, but the key is the resolution within this, is that it's like you have a picture of the Empire State Building, but you could zoom in. You know, like on CSI, they'd always say, you know, refine that image, and it's just, you know, and like you can see the guy's mustache and everything. You can do that with the images that we're making from this, where you can zoom down to see individual stars in something that's, you know, several full moons across. We calculated what it would take to print this out if we wanted to, like, people were like, yeah, we should print a poster, okay? and the poster would be more than 3 stories high at normal printing resolution. So we're not making a poster. But what we are making are movies, okay? So here is my colleague Anil Seth at University of Utah put this together. This is a ground-based image by that guy Robert Gendler, that really good astrophotographer. We're going to zoom in. Oh, look, it's blue. It's a star-forming region, right? You can already see it. You can see the dust from all the cold, dense gas in there. It's all still the ground, okay? And then it's going to stop, put on the brakes, and then we're going to the Hubble image, and it just looks grainy. And we're going to zoom in, and my poor computer is probably like steaming at this point. You can see it twinkling in despair on this. And we're going to zoom in, and you can start to see how that thing that was just, it's starting to see all the individual little stars within it. It's one of these stellar clusters. You see the hot red stars. You see the bright blue stars. Sorry, not the hot red stars, the cool red stars that are bright. You can see the whole mix of everything you've learned about all just played apart in these images. I'm now going to show you just a zoom in just to that one region, but we're now going to zoom in and pan across so you can see it. I married a film video producer, so yeah. Okay, so we're going to zoom in, and then we're going to pan across to that star-forming region just so you can. Can we get the lights? Is this easy to just shut the lights? I should probably get sound for this. Right? Do you see how the whole mix of stars is changing from region to region? I have a student who's taking little groups of stars and making movies of this, of all the past star formation, that she's analyzing each one of those plots of color versus brightness to figure out the history of each little subregion. And we're using this for all kinds of things. And this is our way of understanding how massive galaxies do things, right? I'll just show you a couple more pictures at this point. This is this is part of sort of a region closer to the center of the galaxy. You can see it's a very high density of stars. You zoom in right here. There's a little, this is what we call a little globular cluster. But the stars are these stars, even though this galaxy is really close, you still need the Hubble Space Telescope to pull them apart because the density is so high in massive stars, in massive galaxies. Here's sort of the outer disk. I'm going to zoom in on this region right here. Look at the background galaxy. You can see galaxies that look like whole Hubble Space Telescope images just on their own, peeking through, right? You're looking at a galaxy through another galaxy. It's really neat, okay? You can put together these beautiful large-scale mosaics. This is just showing an image that we take through one filter, and I've just done it this way so that you can see all of this dust in here that is our tracer of where all the cold gas is. So we can actually, even though we're taking images of 0.15 billion stars, we actually can learn a huge amount about what's happening with all the cold gas in here, the fuel for the star formation. So we can track what happens with the fuel, and then we can measure where the stars actually form. So we get the whole life cycle just with this one data set. Anil Seth, who made the movie, what he did is he took that plot of color versus brightness and said, I'm going to grab regions where I know it's only old stars, and I'm going to grab regions where I know there's only young stars. And you can see he did this like a year ago, and so there's holes in it because we hadn't finished at that time. And you can see how smooth the old stars are, where the young stars is very, very patchy all throughout the galaxy. And these are the kinds of analyses that we're doing with this. I have another colleague who's using all of this data that we have with all these different cameras and actually fitting for the properties of every single star, not just what does the distribution in color and luminosity, color and brightness of the stars, but actually this star is exactly this temperature and exactly this bright. And then she's making maps of where these individual stars lie. And so here they've color-coded by exactly how young and thus exactly how massive these individual stars are. And so you can see this kind of the growth and the play of how all of these stars formed over this region. However, if you look at the very center, you can see individual stars, but really not that many. So this galaxy is as close as you can possibly get for a massive galaxy, outside, other than the Milky Way. And even with the Hubble Space Telescope, in the very center region, we still have a really hard time figuring out what's going on. And this is the first region of where galaxies formed. So even the Hubble Space Telescope isn't yet telling us what's going on there. So I have a dream, okay? My dream is I don't want this in space. I want that in space, okay? If I had that bigger one, I could then pick that stuff apart and I could finally see into the very centers of very, very massive galaxies. Because if you think about it, the Hubble Space Telescope, it was built in 1986. It is an old instrument. The equivalent of 1986 Toyota in space, okay? It's well maintained, it's taken to the car wash, they've had it detailed, they've spiffed up the engine, they've replaced the rotors and the pads at a regular basis. It's not gonna go forever, okay? So my goal is, my next big thing is trying to think about how do we get a replacement for that. Okay, so I just want to thank you.
Take a couple of questions, and then there'll be time to talk to Professor Dalcanton afterwards if there are additional questions. Anybody have one? Go ahead, sir.
Yeah, thank you very much.
Oh, no, my pleasure.
You talked about not being able to see in the middle of Andromeda with the Hubble Space Telescope. How come we can't be able to resolve what they were doing with the black hole?
The center of the Milky Way, it's a lot closer.
So it's fact that it's closer.
It's just that it's right. So if I took Andromeda and I moved it really close, those stars would get, if I moved it as close as the center of the galaxy, I'd be able to see in just fine. And we can see some stars, but it's only the brightest ones. So those plots showing all the colors and brightnesses, you could see the ones that are at the very, very, very top, and you can learn something from that. We didn't learn nothing, but you really want, I want to see all that stuff down there.
Do you expect to be able to do similar stuff to what Andrea did? Try to find the location of the...
Well, people have already found it because it's the center of Andromeda, and it is one of the first things that was done with the Hubble Space Telescope was very early on, was look at the very center of Andromeda. And it turns out it's got this crazy double thing. You kind of expect to see one bright spot, and instead you see two. And the brightest spot doesn't actually seem to be the center. And there's this weird accretion disk thing where material, it's very complex, and people have worked very hard to try to understand it. So we have seen the area around it, but for those of you, Andrea gets, since she was a graduate student, has been tracking the positions of stars near the center of the Milky Way, where we think there's a black hole. And she can watch these stars, because she's been studying this for decades. She can watch these individual stars as they slingshot around the black hole. And they have some candidates where one day they think it's going to go in. Right, so it's really, it's absolutely amazing work. I don't know that we'll ever be able to track individual stars over, because some of those stars she's looked at are very faint, and the faint stars are the ones that kind of disappear faster than the bright ones. It would be cool though.
One more question. Go ahead.
You talked about behind nebula and other things in our galaxy that have names. Has anybody taken a look at what you photographed in Andromeda and named things there?
There's a couple of features to Andromeda. There's the 10 kiloparsec ring, star-forming ring, which is, a lot of the star formation tends to be in this one ring. Some people, when they're writing enthusiastic proposals, have been known to call it the ring of fire. And that has a mixed level of success, right? I mean, the last thing you want is people judging your work kind of cackling a little bit at what you chose to call something. And we have, my whole life, I've always been somebody who's interested in large samples of things where you don't care as much about the individuals. And it's very strange for me to be working on something where you show me part of it. It's like, oh yeah, that's that place where this thing splits, and there, I've gotten very personal with this for the first time in my life. So that's an interesting question. I'll have to think about it. That's unexplored territory.
Okay, on behalf of the Center for Cosmology and Astroparticle Physics, I would like to thank you, the audience, for your time,
Yeah, thank you very much.
and attention. And we'd like to thank Professor Dalcanton for delivering this awesome lecture.
Oh, look at
We got
that.
our plaque. For those of you who have more questions, I encourage you to come talk to her afterwards. And for those of you who'd like more information about our other activities, including another public lecture on Sunday, we have a table outside with lots more information. So thank you. Good night.
I haven't got one of these since high school. This was like